Well, thank you very much for inviting me for this talk. I'd like to present my work here in Brazil about laser-assisted materials processing from the melt. So the topics that I will cover on this talk is, first of all, who I am and where am I, why using lasers for material processing. The three techniques that I would like to talk to you is laser-heated pedestal growth, aerodynamic levitation, surface heat treatment. Then we talk about some conclusions and, of course, the acknowledgements. Okay. So, who am I and where am I? My name is Marcello Andreeta. I am an associate professor at Materials Engineering Department here in Brazil at the University Federal of São Carlos. And my main line of work, my line of research is photonic materials processing, laser and microwave using to processing materials. The focus is on clean energy, harvesting, generation, efficiency, single crystals, oxide glasses, composites, and of course, any possible devices that could arise from those researches, okay? Just to let you know where am I, so you can see here is Europe and you are in Amsterdam, at least, I know. Now we can travel a little bit. You can see here the South America and the Amazon capital there. And here am I in São Carlos at the bottom of Brazil. Okay. So just to let you, just a curiosity, from the capital of Amazon, the rainforest, to São Carlos is about 2,500 kilometers. And from Amsterdam to the same capital is about 8,500. So it's about 1/3 the distance. So we are all far away from the rainforest, just to let you know. This is our city. It's about 250,000 people. The temperature is average from 9 to 29 degrees. It's not as hot. Well, today is very hot, but normally it's okay, the temperature. So it's known as Brazil's technology capital. So there's a lot of students and many universities in this city. This is our materials engineers department, just to let you know how it was founded in 1972. This is quite old for Brazilian standards, and it's the pioneer in material science and engineering in Latin America. It researches mainly in metals, polymers, and ceramic materials. Well, why lasers we would like to talk? Let's try to explore ceramic materials, for instance, okay? What you would like to have a technique to prepare ceramic materials? The first one, that should be no temperature limitations, right? Because ceramic materials have very high melting points. Should be a fast process. For research, it's good to use small quantities of materials. And of course, should be at low cost for buy it, okay? So if you combine all these features, you reach laser heating techniques that can satisfy all these conditions, right? And through laser heating technique, you can explore new and conventional single crystals, new glass compositions, and of course, produce a fast and localized surface heat treatment. So this could lead to new miniature or design devices. Once you found the new possible devices that you can apply or interested in produce, you can return to the top and explore another material that can make it even better, okay? So this is a very fast and very powerful technique. Okay. The first technique that I would like to talk to you that we have here is the laser heated pedestal growth technique that we were one of the pioneers on this technique worldwide, okay? And this technique is basically a very small, tiny floating zone technique where you use the laser as a heating device. So we have, let's say, a solid cylinder of laser. When passes through these optical components, a reflexcon, it converts it expands its radius and convert it to a hollow cylinder, okay? Then you can reflect and direct the laser to a focusing mirror, and this will lead to a ring-shaped focus on the surface of the material that you would like to melt. So these are the steps. You have the mechanical alignment of a seed and a pedestal. Pedestal is the material that you would like to melt, okay? And then you can create a small volume of molten material on the top of the pedestal. Then you can touch the seed on this melt, and then now you have a liquid phase that is kept glued to the solid phase to surface tension, and you don't have crucibles here. So you can reach any temperature possible for this compound, okay? Then you can start the pooling. Here is the photograph. This is about 1 millimeter size. So the drawback is small samples, but it's not a drawback for say, because we would like to have miniaturized devices. So one thing compensates the other, okay? What we discover is that you don't have to pre-react the compound that you like to grow or melt, okay? You can use just a mixture of oxides with an organic ligand, such as polyvinyl alcohol. So you can create a small pedestal just with a mixture of the powders on the stoichiometric that you would like to have, okay? So in this way, you can, in one process, you can liberate the organic, pre-react your material, melt it, and crystal grow it, okay? And we have automatic diameter control. It's an artificial vision system based, and we can look at the molten zone and compare and try to stabilize its parameters. So here you can see when the control is activated, the diameter is almost constant. And when it's deactivated, of course, because of the laser fluctuations and overall other factors, such as growing crystal, you need more power. You have a diameter that fluctuates along its growth, okay? So here we have, just to demonstrate the efficiency of this kind of control diameter system, we have here a pedestal that is provoked with some fluctuations mechanically, and here's the fiber grown from those pedestals, and you can see that a 20% diameter fluctuation is reduced to less than 2%, even with a very strong out of equilibrium system, okay? So this laser technique has a threefold feature that must satisfy, and we can extract some information from these threefold features, okay? First of all is the wetting angle. The wetting angle for each material has a wetting angle that will keep all the surface tensions in equilibrium, okay? So if you keep this angle constant, this is the challenge. If you keep this angle constant, the diameter of the crystal grown will be constant. But the pedestal is not perfect, so it fluctuates. So you need to compensate that. That's why we have a diameter control system. By mass conservation, if you consider that all material that is growing, is melting, is growing from in a single crystal, you can extract the radius of the fiber as a function of the radius of the pedestal and the relationship between the pooling speeds. And through the heat energy conservation, that's the important thing, you can extract, for instance, the temperature gradients at the solid-liquid interface, where you can predict the maximum diameter of the crystal that you can produce without cracks. So here we have two examples of lithium niobate and tantalum oxide, where we can see that the maximum diameter is exceeded only for the fiber radius greater than 460 micron, okay? And for tantalum oxide is a little bit higher, it's about 1.1, the radius of the maximum diameter that you can extract without crack. So these are some crystals or materials that we can produce in our lab, and you can see that this technique is very versatile. So you can produce materials with low melting point, it's lower for us, okay, it's about 800 degrees Celsius, to zircon oxides, such as near 3000 degrees Celsius. So you can explore a huge amount of compounds in a single crystal form. About aerodynamic fluctuation, what is this? you have a small piece of material and spheroid you can put here in a cone where you have a gas flux here, okay? And this kept this spheroid fluctuating through this aerodynamic system here. So it doesn't touch anything on the system. It fluctuates on a mattress of air. Then you can focus a laser beam on the top of this material and melt this ball here, this small piece of material, and create a sphere, a molten sphere. If you cool this very fast, then you can make a glass of it. So you can see here, we have about 1 millimeter size sphere with, this is a natural polishing, a fire polishing of the material, see? And it's already polished for you, so to make a measurement. You can see here the focus of the flashlight. So it's quite good optical quality. And of course, if you have a double diameter, you have a smaller cooling rate, right? If you have a small diameter, you have a fast cooling rate. And here we have two processes that I would like to show you. If the cooling rate is higher than the critical cooling rate, you have a glass. So this is an actual experiment, see, of a barium titanate silicate glass. We have a filter. We can remove the filter to see in low temperature. Now the laser is turned off. You have a glass there, so you can pick up the glass. But if you do the same thing, but with a different cooling ratio, you see the textbook thing here, that this is a crystallization. So it was going to make a glass, but something crystallizes. Then everything must crystallize first, then you can cool down everything again. So it's very nice for students to see this technique. About the surface heat treatment, we have also in our lab. So we have two galvanometric mirrors that is computer controlled, so you can make any drawings or treatment lines or everything on the surface of compounds, mainly on glass we are working with. So here you can see two different approaches on heat treatment on glass. So you have micro lenses created through a very fast heating. So you expand the volume of the glass locally and you create a Gaussian shaped lens. But if you increase the size of those lenses, you create a dimple because it cannot sustain itself anymore. So it make a little dimple on the top. So when you pass light through it, you can make a QR code of this compound. But if you don't have dimples, you have a very clean shaped, so easy to measure. But if you have dimples, you can see here the interference pattern created by those dimples. Okay, this is just to show the heat treatment. Of course, if you have a very high power and a traveling focus beam here in low speed, you create a very large heated affected zone. On other array, if you just reduce a little bit but create a very fast, you can see that the depth of the heated affected zone decreases very, very much. So it's interesting to do experiments on that. And another example of the heat treatment is that you can create lines of crystallized material. So you can make a vitroceramic on a glass, localized vitroceramic. So here we have a glass that has its composition on an eutectic point on the phase diagram from silicate calcium and silicate lithium. And then you can see it when you have a very fast line passing through the surface of the glass. We have a very aligned microstructure with the two phases. And when you're decreasing, this disorganized, okay? And this the average mean space between the phases, it follows the Jackson-Hunt. So it's really an eutectic material. So just on two more slides, the surface heat treatment on thick films. You can make a ceramic. You can show that when you heat treat a thick film, ceramic thick film, you have a two-step process. And from the devices, we can make composites in situ. So you can just produce two phases correlated in situ. Or you can use the fiber to induce a crystallization on a ceramic during heat treatment. This creates a single crystal that can link two electrodes, for instance, without any grain boundary. That's interesting that you can increase or improve about 250% the ionic conductivity on those materials. The micro heating devices, we use sapphire fibers to guide the light. And if you put rare earth on the sapphire, you know it will all segregate to the liquid. You get the pure sapphire. But if you grow on the top of the sapphire optical fiber, you can grow a different compound with a very high concentration of rare earth. And in this way, you can make a localized heating, such as this. You can input light here. In t equals 0 seconds, it started. You have here egg white that's similar to the conductivity of the human tissue. And after 1 minute irradiating, you can see that you can make a large heated effector zone. So this for medicine might be a very important micro device. So here is the temperature along with the nominal laser power to the input. So you can reach above 60 degrees in egg white. That's interesting. Another thing that you can do with the applications is the laser heat pedestal grow with the temperature measurements for high temperature measurement, where you put a ruby on a point of the sapphire. And now you measure the lifetime decay of the chromium on this ruby. So you can correlate the lifetime with the temperature. So you can create a thermometer on this, okay? And of course, solid state lasers, when you can create any materials and try to laser it and make different colors and work on that, okay? So the conclusions. The laser is a very versatile technique to explore ceramic materials. It's ideal for material science and engineering. Small amounts of materials needed. That's very nice for low-cost technique. No temperature limitation, but as a drawback, you have characterization challenges due to the small size. So this, of course, allows also the development of new miniature and devices for this material. I would like to show this phrase that's from Tadahiro Sekimoto. That's those who dominate materials dominate technology. That's our motto here. And of course, I'd like to thank our postgrad program, CAPS, CNPq. Alacer is a company that finances us, and FAPESP, that is a government agency that finances lots of grants for us, okay? Thank you for listening, and sorry.